Secretion of bile by the liver. Functions of the biliary tree. One of the many functions of the liver is to secrete bile, normally between 600 and 1000 ml per day. Bile serves two important functions. One, bile plays an important role in fat digestion and absorption because bile acids in the bile do two things. Number one, they help to emulsify the large fat particles of the food into many minute particles, the surface of which can then be attacked by lipase enzymes secreted in pancreatic juice. And two, they aid in absorption of the digested fat and products through the intestinal mucous membrane, right? And the another function is bile serves as a means for excretion of several important waste products from the blood. This includes especially bilirubin, which is an end product of hemoglobin destruction, and excesses of cholesterol is excreted through the bile. Bile acts as a means for the excretion of waste products, for example, bilirubin and excess cholesterol. Physiologic anatomy of biliary secretion. Bile is secreted in two stages by the liver. Number one, the initial portion is secreted by the principal functional cells of the liver, that is the hepatocytes. This initial secretion contains large amounts of bile acids, cholesterol, and other organic constituents. It is secreted into minute bile canaliculi that originate between the hepatic cells. Right? These bile acids aids in two functions. One is emulsification of the fats. Second one is absorption of the digested fat and products. Right? And two, option number two. What is the second stage of secretion of bile by the liver? That is, next the bile flows into the bile canaliculi toward the interlobular septa, where the canaliculi empty into terminal bile ducts, and then progressively larger ducts finally reach the hepatic duct and common bile duct. From these, the bile either empties directly into the duodenum or is diverted for minutes up to several hours through the cystic duct into the gallbladder as shown in the figure 69.2. See figure 69.2, showing the liver secretion and gallbladder emptying. You can see in the liver bile acids via blood stimulate parenchymal secretion. You can see the bile may empty directly into the duodenum, or it may be diverted into the gallbladder via the cystic duct. Right? Bile in the gallbladder, bile is stored and concentrated up to 15 times in gallbladder. See, and you can see this arrow mark in the top left one. Secretin via bloodstream stimulates liver ductal secretion. Right? Now, in the gallbladder shown in the top right side, vagal stimulation causes weak contraction of gallbladder, and you can also see in the extreme bottom one, the cystokinin via blood stream causes gallbladder contraction, and 2 relaxation of sphincter of OD. You can see this in this picture, the stomach structure, liver structure, and duodenum structure, and pancreas structure, and the acid that is gastric, that is hydrochloric acid in the stomach, right? When it goes through the bile ducts, a second portion of the liver secretion is added to the initial bile in response to secretin, which is a local hormone. This additional secretion is a watery solution of sodium and bicarbonate ions secreted by secretory epithelial cells that line the ductules and ducts. This second secretion somewhat increases the total quantity of bile by as much as an additional 100%. Now let's talk about the storing and concentrating bile in the gallbladder. The bile is secreted continually by the liver cells, but most of it is normally stored in the gallbladder until needed in the duodenum. The maximum volume that the gallbladder can hold is only 30 to 60 milliliters. Nevertheless, as much as 12 hours of bile secretion, usually about 450 milliliters, can be that is can be stored in the gallbladder because water, sodium chloride, and most other small electrolytes are continually absorbed through the gallbladder mucosa, concentrating the remaining bile constituents that contain the bile salts, cholesterol, lecithin, and bilirubin. Most of this gallbladder absorption is caused by active transport of the sodium through the gallbladder epithelium, and this is followed by secondary absorption of chloride ions, water, and most other diffusible constituents. Bile is normally concentrated in this way about 5-fold, but 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 it can be concentrated up to a maximum of 12-fold. Now let's talk about the composition of the bile. The table 69.1 gives the composition of bile when it is first secreted by the liver and then after it has been concentrated in the gallbladder. This table shows that by far the most abundant substances secreted in the bile are bile salts. Note that the most abundant substances in the bile are bile substances, right, which account for about one half of the total solutes also in the bile. Also secreted or excreted in large concentrations are bilirubin, cholesterol, lecithin, and the usual electrolytes of the plasma. You can see this composition of the liver when it is secreted by the liver, and after it is being concentrated in the gallbladder. The constituent, as usual, it has water, and the more amount is by the bile salts, and then the other waste products such as bilirubin, excess cholesterol, fatty acids, lecithin, and other normal electrolytes is seen in this bile. Important role is played by the bile salts. Now let's talk about the concentration. Now let's talk about the emptying of the gallbladder. Stimulatory role of cholecystokinin. When the food begins to be digested in the upper gastrointestinal tract, The gallbladder begins to empty, especially when the fatty food reaches the especially when the fatty foods reaches the duodenum about 30 minutes after a meal. About 30 minutes after a meal, the mechanism of gallbladder emptying is rhythmical contractions of the wall of the gallbladder, but effective emptying also requires simultaneous relaxation of the sphincter of Oddi, which guards the exit of the common bile duct into the duodenum. Sphincter of Oddi guards the exit of the common bile duct. Common bile duct into the duodenum. Common bile duct into the duodenum. Right, by far the most potent stimulus for causing the gallbladder contractions is the hormone cholecystokinin. You can see cholecystokinin causes the gallbladder contraction, right? This is the same cholecystokinin discussed earlier that causes increased secretion of digestive enzymes by the acinar cells of the pancreas right, and the stimulus for cholecystokinin entry into the blood from the duodenal mucosa. The stimulus for the entry of the cholecystokinin into the blood from the duodenal mucosa is mainly the presence of fatty foods in the duodenum. The gallbladder is also stimulated less strongly by acetylcholine. The gallbladder is also stimulated less strongly by acetylcholine secreting nerve fibers from both the vagus and the intestinal enteric nervous system. We can see in the figure 69.2 summarizes the secretion of bile, its storage in the gallbladder, and its ultimate release from the bladder to the duodenum. We can see the release of the bile from the gallbladder is caused by 1. By the vagal stimulus causes weak contraction of the gallbladder, or the cholecystokinin stimulation causes the potent contraction of the gallbladder and the relaxation of the sphincter of Oddi, thus by causing the release of bile into the duodenum. Right. Now let's talk about the functions of bile salts in fat digestion and absorption. The liver cells synthesizes about 6 grams of bile salts daily, right? The precursor of the bile salts is cholesterol, which is either present in the diet or synthesized in the liver cells during the course of metabolism. Cholesterol is present either in the diet or is synthesized in the liver cells during the course of fat metabolism. The cholesterol is first converted to cholic acid. Or chenodeoxycholic acid, and in about equal quantities. These acids in turn combine principally with glycine and to a lesser extent with taurine to form glyco and taro conjugated bile acids. Right? The salts of these acids, mainly sodium salts, are then secreted in the bile. Right? The bile salts have two important actions in the intestinal tract. What is that? First, they have a detergent action on the fat particles in the food. This decreases the surface tension or inter this decreases the surface tension of the particles and allows the agitation in the intestinal tract to break the fat globules into minute sizes. This is called emulsifying or detergent function of the bile salts. This is called emulsifying or detergent function of the bile salts. Second, and even more important than emulsifying or detergent function of bile salts is bile salts helps in the absorption of fatty acids, monoglycerides, and cholesterol and other lipids from the intestinal tract. They do this mechanism. They do this by forming small physiological complexes. They do this by forming small physical complexes with these lipids. The complexes are called micelles, 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 and they are semi-soluble in the chyme because of the electrical charges of the bile salts. The intestinal lipids are ferried. The intestinal lipids are ferried in this form. How? By forming the micelles. In this form means in the form of micelles. The intestinal lipids are ferried in this form to the intestinal mucosa, where they are then absorbed into the blood, as will be described in detail in chapter 72. Without the presence of bile salts in the intestinal tract, without the presence of bile salts in the intestinal tract, up to 40% of the ingested fats are lost into the feces, and the person often develops a metabolic deficit because of this nutrient loss. Without the presence of bile salts in the intestinal tract, up to 40% of the ingested fats are lost into the feces, and the person often develops a metabolic deficit because of this nutrient loss. Let's talk about the enterohepatic circulation of bile salts. Enterohepatic means from the liver to the intestine. How these bile salts are being circulated. About 94% of the bile salts are reabsorbed into the blood from the small intestine. About one half of this is by diffusion. About one half of this by diffusion through the mucosa in the early portions of the small intestine, and the remainder by the active transport process through the intestinal mucosa in the distal ileum. Right? They then enter the portal blood and pass back to the liver. They then enter the portal blood and pass back to the liver. On reaching the liver, on first passage through the venous sinusoids, these salts are absorbed almost entirely back into the hepatic cells and then resecreted into the bile. Right? Resecreted into the bile. This is called enterohepatic circulation. From the liver into the small intestine, from the small intestine back into the blood, that is portal blood, from portal blood into the liver, again liver into the intestine. This is enterohepatic circulation. In this way, about 94% of all the bile salts are recirculated into the bile. So on the average, these salts mark the entire circuit some 17 times before being carried out in the feces. The small quantities of bile salts lost into the feces are replaced by new amounts formed continually by the liver cells. This recirculation of the bile salts is called the enterohepatic circulation of the bile salts. The quantity of bile secreted by the liver each day is highly dependent on the availability of bile salts. The greater the quantity of bile salts in the enterohepatic circulation, usually a total of only about 2.5 grams, the greater the rate of bile secretion. The greater the rate of bile secretion. The rate of bile secretion depends on the availability of bile salts. The greater the quantity of bile salts in the enterohepatic circulation, the greater the rate of bile secretion. Indeed, ingestion of supplemental bile salts can increase bile secretion by several hundred milliliters per day. Indeed, ingestion of supplemental bile salts can increase bile secretion by several hundred milliliters per day. If a bile fistula empties the bile salts to the exterior for several days to several weeks, so that they cannot be reabsorbed from the ileum, the liver increases its production of bile salts from 6-fold to 10-fold, which increases the rate of bile secretion most of the way back to the normal. This demonstrates that the daily rate of liver bile salt secretion is actively controlled by the availability of bile salts in the enterohepatic circulation. The daily rate of liver bile salt secretion is actively controlled by the availability of bile salts in the enterohepatic circulation. Now let's talk about the role of secretin in controlling bile secretion. In addition to the strong stimulating effect of bile salts to cause bile acids to cause bile secretion, the hormone secretin that also stimulates pancreatic secretion increases bile secretion, sometimes more than doubling its secretion for several hours after a meal. This increase in secretion is almost entirely secretion of a sodium bicarbonate rich watery solution by the epithelial cells of the bile ducts, and not increased secretion by the liver parenchymal cells themselves. The bicarbonate in turn passes into the small intestine and joins the bicarbonate from the pancreas in neutralizing the hydrochloric acid from the stomach. Thus, the secretin feedback mechanism for neutralizing duodenal acid operates not only through its effects on pancreatic secretion, but also to a lesser extent through its effect on secretion by liver ducts and ducts. Now let's talk about the liver secretion of cholesterol and gallstone formation. right? Bile salts are formed in the hepatic cells from cholesterol, right, in the blood plasma. In the process of secreting bile salts, about 1 to 2 grams of cholesterol are removed from the blood plasma and secreted into the bile each day. Cholesterol is almost completely insoluble in pure water, but the bile salts and lecithin in bile combine physically with the cholesterol to form ultramicroscopic micelles in the form of colloidal solution. When the bile becomes concentrated in the gallbladder, the bile salts and lecithin become concentrated along with the cholesterol, which keeps the cholesterol in solution. Under abnormal conditions, the cholesterol may precipitate in the gallbladder, resulting in the formation of cholesterol gallstones, as shown in the figure 69.4. The formation of gallstones. See how it forms. Causes of gallstones is: one is too much absorption of water from the bile, two, too much absorption of bile acids from the bile, three, too much cholesterol in bile, and four, inflammation of epithelium results in the formation of cholesterol gallstones, right? Now courses followed by the bile: 1 indicates during rest, 2 during digestion. During rest it goes to the gallbladder, or during digestion it goes to the duodenum, right? You can see the structure showing the gallbladder, liver, and papilla of water, and cystic duct, and common bile duct, and sphincter of Oddi, and pancreatic duct, and stones, right? The amount of cholesterol in the bile is determined partly by the amount of fat that the person eats, because liver cells synthesize cholesterol as one of the products of fat metabolism in the body. For this reason, people on a high fat diet over a period of years are prone to the development of gallstones. For this reason, people on a high fat diet over a period of years are prone to the development of the gallstones. Now, because one of the functions of the liver is to form the cholesterol, inflammation of the gallbladder epithelium, often resulting from a low-grade chronic infection, right, may also change the absorptive characteristics of the gallbladder mucosa, sometimes allowing excessive absorption of water and bile salts, but leaving behind the cholesterol in the gallbladder in progressively greater concentrations results in the formation of cholesterol gallstones. What are the causes of gallstones? One is too much absorption of the water and bile salts from the bile in the gallbladder mucosa, and two is inflammation of the gallbladder epithelium due to low-grade infection, and too much of cholesterol in the bile. Why it is too much of the cholesterol in the bile? Because one of the functions of the liver is to form the cholesterol, which is it is more seen in patients patients or persons taking the high fat diet over a period of years. Then the cholesterol begins to precipitate, first forming many small crystals of cholesterol on the surface of the inflamed mucosa, but then progressing to large gallstones. Now let's see. Now let's have a look over the measurement of bilirubin in the bile as a clinical diagnostic tool. Till now we have discussed about bile salts importance and the cholesterol. What happens? It becomes excess in the gallbladder, and what is the importance of. Now have a look over the bilirubin, which is one of the waste products of the liver. Waste products is cholesterol, bilirubin, waste products. In addition to bile salts, many substances are excreted in the bile and then eliminated in the feces. For example, water, bilirubin, excess cholesterol, and some electrolytes. One of these is the greenish yellow pigment called bilirubin. This is a major end product of hemoglobin degradation as pointed out in chapter 19. However, it also provides an exceedingly valuable tool for diagnosing both hemolytic blood diseases and various types of liver diseases. It is helpful for diagnosing hemolytic blood diseases and various types of liver diseases. Therefore, while referring to figure 69.5, let us explain this. This is the figure 69.5 showing the bilirubin formation and secretion. Let's have a discussion on some other topic, such as briefly when the red blood cells have lived out their lifespan on an average of 120 days and have become too fragile, too breakable to exist in the circulatory system and become too fragile to exist in the circulatory system, their cell membranes rupture and the released hemoglobin is phagocytized by the tissue macrophages. For example, reticuloendothelial system throughout the body. The hemoglobin is first split into globin and heme, and the heme ring is opened to give one free iron, which is transported in the blood by transferrin, and a straight chain of 4 pyrrole nuclei, which is the substrate from which bilirubin will eventually be formed. The first substance formed is biliverdin, but this is rapidly reduced to free bilirubin, right? Also called unconjugated bilirubin, which is free bilirubin or unconjugated bilirubin, which is gradually released from the macrophages into the plasma. This form of bilirubin, that is free bilirubin, immediately combines strongly with plasma albumin and is transported in this combination throughout the blood and interstitial fluids. Within hours, the unconjugated bilirubin is absorbed through the hepatic cell membrane. In passing to the inside of the liver cells, it is released from the plasma albumin. And soon thereafter conjugated about 80% with glucuronic acid to form bilirubin glucuronide about 10% with sulfate to form bilirubin sulfate and about 10% with a multitude of other substances. In these forms, what are these forms? Bilirubin glucuronide, bilirubin sulfate, and some other form. In these forms, the bilirubin is excreted from the hepatocytes by an active transport process into the bile canaliculi and then into the intestines. Now have a look over the formation and fate of urobilinogen. Urobilinogen. Once in the intestine, about half of the conjugated bilirubin is converted by bacterial action into the substance urobilinogen, which is highly soluble. Some of the urobilinogen is reabsorbed through the intestinal mucosa back into the blood. Most of this is re-excreted by the liver back into the gut, but about 5% is excreted by the kidneys into the urine. After exposure to air in the urine, the urobilinogen becomes oxidized to urobilin. Alternatively, in the feces, it becomes altered and oxidized to form stercobilin. These interrelations of bilirubin and the other bilirubin products are shown in figure 69.5. Let's have a look over the figure 69.5. In the plasma, what happens? Fragile red blood cells were ingested by reticuloendothelial system. They are broken down into the heme and globin, right? Now the heme, by the action of heme oxygenase, is converted into biliverdin. Biliverdin is converted into the free bilirubin or unconjugated bilirubin. It enters into the liver. In the liver, it is when it is in the liver, it is converted into the conjugated bilirubin, right? Conjugated bilirubin is converted into the urobilinogen. The urobilinogen is converted into the stercobilinogen, which upon oxidation is converted into the stercobilin, which is excreted via the feces, right? Some amount of the urobilinogen is absorbed from the liver and is excreted into the kidney and is excreted via the kidneys. Urobilinogen on exposure to air in the kidneys, it is converted into the urobilin and is excreted via the urine, right? This is how the bilirubin is formed and secreted. Now let's have a discussion about the clinical applications of this bilirubin. Jaundice, where there is excess bilirubin in the extracellular fluid, right? Jaundice refers to a yellowish tint to the body tissues, including yellowness of the skin and deep tissues. This has been explained in detail in chapter 23. In jaundice, what happens? There is a excess bilirubin in the extracellular fluid.